Today we are going to learn about precision recall and imbalanced datasets, best practices, focusing on strategies to improve model performance in skewed data scenarios common in data science.
Welcome to our video on precision recall and imbalanced datasets, best practices. In this session, we'll explore the complexities of handling precision recall trade-offs when dealing with imbalanced datasets, a prevalent challenge in data science. Understanding these concepts is crucial for ensuring that our models are not only accurate but also effective when the class distribution is heavily skewed. We'll cover various strategies, from rebalancing datasets to using synthetic data like SMOTE and adjusting decision thresholds. By the end of this video, you'll be equipped with practical insights to enhance model performance, particularly in real-world scenarios like healthcare data. Let's dive in.
Imbalanced datasets occur when one class in the target variable significantly outnumbers the other. This imbalance poses a serious challenge for machine learning models, which tend to be biased towards the majority class, often leading to misleading accuracy metrics. In a binary classification, if 95% of the data belongs to one class, a model predicting the majority class for every instance would be 95% accurate, but essentially useless. This highlights the need for metrics beyond accuracy, such as precision and recall. Precision measures the accuracy of positive predictions, while recall measures the ability of the model to find all relevant cases within a dataset. Therefore, understanding these challenges is critical for developing effective models in scenarios like fraud detection or medical diagnosis, where the minority class is often of greater interest.
In skewed datasets, precision and recall become vital metrics for evaluating model performance. Precision is crucial when the cost of false positives is high, as it measures the correctness of positive predictions. Conversely, recall becomes important when missing a positive instance is costly, as it reflects the model's ability to detect all positive instances. For example, in medical testing, high recall ensures that all potential cases are flagged, minimizing the risk of missing a diagnosis. However, this often comes at the expense of precision, leading to more false positives. Thus, balancing precision and recall is a complex yet essential task, depending on the specific context and goals of your analysis. Rebalancing datasets is a fundamental strategy to address the challenges of imbalanced data. The two primary techniques are oversampling the minority class and undersampling the majority class. Oversampling involves duplicating instances of the minority class to balance the dataset, which can lead to overfitting. Undersampling, on the other hand, reduces the number of majority class instances, which might result in loss of valuable information. Hybrid methods combine both approaches, attempting to capitalize on their strengths while mitigating their weaknesses. Each method impacts model training differently, and the choice of technique should be guided by the specific dataset and problem context. Experimenting with different strategies is often necessary to achieve optimal results. Synthetic minority oversampling technique, SMOTE, is a popular method for generating synthetic data to address imbalance in datasets. SMOTE creates synthetic instances of the minority class by interpolating between existing instances. This approach can help improve model accuracy and robustness by providing more diverse examples for training. However, SMOTE is not without limitations. It can introduce noise and doesn't consider the distribution of the majority class, which can result in less realistic synthetic examples. Beyond SMOTE, advanced techniques like adaptive synthetic sampling, ADASN, and borderline SMOTE offer more nuanced approaches by focusing on more difficult to classify examples or adjusting the level of synthetic data generation based on learning difficulty. Threshold adjustment is a powerful technique for managing precision recall trade-offs. By default, many classification models use a 0.5 threshold to distinguish between classes. However, this may not be optimal for imbalanced datasets. Adjusting thresholds allows you to control the sensitivity and specificity of your model. Lowering the threshold increases recall, capturing more positive instances at the risk of more false positives. Conversely, raising the threshold enhances precision, reducing false positives but potentially missing true positives. Carefully tuning the threshold based on the context and goals of your analysis can significantly improve model performance. Practical considerations include the use of cross-validation to evaluate different thresholds and the potential need to adjust thresholds dynamically in response to changing data distributions.
Precision recall curves are a crucial tool for evaluating models on imbalanced datasets. These curves plot precision against recall for different threshold values, providing a comprehensive view of model performance. The shape of the curve reveals the trade-offs between precision and recall, guiding decisions about which model to select based on specific needs. The area under the curve, AUC, of a precision recall curve is a summary metric that helps compare models. A higher AUC indicates better performance. Precision recall curves are especially useful when the positive class is of primary interest, offering insights that traditional raw curves might miss in skewed data scenarios.
Healthcare data often presents unique challenges due to its inherent imbalance. Diseases like cancer can have low prevalence rates, making precision recall metrics critical in model evaluation. In healthcare, high recall is essential to ensure all potential cases are flagged, though it may lead to increased false positives. Consider a case study in disease prediction, where the goal is to develop a model that can accurately identify patients at risk. Strategies include using SMOTE for synthetic data generation and adjusting decision thresholds to balance precision and recall. The impact of these models on patient outcomes can be substantial, offering early intervention opportunities and improving treatment efficacy. Precision recall trade-offs in this context are not merely statistical choices but have real-world implications for patient care and resource allocation.
Handling imbalanced datasets efficiently requires robust tools and libraries. Scikit-learn, a popular Python library, offers many functions for managing imbalanced data, and the Imbalanced Learn extension builds on this foundation with additional functionalities. Key methods include SMOTE, ADASN, and various undersampling techniques, which can be seamlessly integrated into your existing workflows. The library's comprehensive documentation and intuitive API make it accessible even for those relatively new to data science. Effective use tips include experimenting with different rebalancing strategies, leveraging cross-validation for model evaluation, and continuously monitoring model performance to adapt to new data distributions. Mastering these tools can significantly enhance your ability to develop high-performing models in challenging imbalanced scenarios.
In conclusion, managing precision recall trade-offs in imbalanced datasets is a vital skill for data scientists. Throughout this video, we've explored the challenges of skewed data distribution and the importance of precision and recall in model evaluation. Key strategies include rebalancing datasets, using synthetic data like SMOTE, and adjusting decision thresholds. Remember, the best approach depends on the specific context and objectives of your analysis, and continual learning and adaptation are crucial. By applying these best practices, you can significantly improve model performance and ensure that your insights have a meaningful impact on real-world scenarios. Thank you for joining us, and we hope you feel more confident in tackling imbalanced datasets with precision and recall in mind.